large sample distribution of the t-statistic. When n is large, S sub big Y squared is close to sigma sub big Y squared with high probability. Thus, the distribution of the t-statistic is approximately the same as the distribution of open big Y bar minus mu sub big Y naught close over sigma sub big Y bar, which in turn is well approximated by the standard normal distribution when n is large because of the central limit theorem, key concept 2.7. Accordingly, under the null hypothesis, t is approximately distributed big N of 0 and 1 for large n, equation 3.12. The formula for the p-value in equation 3.10 can be rewritten in terms of the t-statistic. Let t superscript act denote the value of the t-statistic actually computed. T superscript act equals big Y bar superscript act minus mu sub big Y naught over the standard error of big Y bar, equation 3.13. Accordingly, when n is large, the p-value can be calculated using p-value equals 2 capital Phi open negative absolute value of t superscript act close parentheses, equation 3.14. As a hypothetical example, suppose that a sample of n equals 200 recent college graduates is used to test the null hypothesis that the mean wage, big E of big Y, is $20 per hour. The sample average wage is big Y bar superscript act equals 22.64, and the sample standard deviation is S sub big Y equals $18.14. Then the standard error of big Y bar is S sub big Y over the square root of n equals 18.4 over the square root of 200 equals 1.28. The value of the t statistic is t superscript act open 22.64 minus 20 close over 1.28 equals 2.06. From appendix table 1, the p-value is 2 phi open negative 2.06 close equals 0.039 or 3.9%. That is assuming the null hypothesis to be true. The probability of obtaining a sample average at least as different from the null as the one actually computed is 3.9%.